In this final section of the unit, we're going to talk about relativistic momentum and energy. The classical equation for momentum will not hold true at relativistic speeds as we approach the speed of light. So we can see that on the graph here. This purple line is our classical understanding of momentum equal to mass times velocity. It's linear relationship here. But you can see that that doesn't happen as the velocity approaches the speed of light. So velocity is bounded by the speed of light. So momentum cannot increase linearly because we can't have a velocity greater than the speed of light. So the equation for relativistic momentum is P is equal to gamma times m times v, where m is the invariant mass, or the mass measured by an observer at rest with respect to the mass. In older texts, relativistic momentum is interpreted to mean that a rapidly moving particle undergoes an increase in mass. This mass is called the relativistic mass and is greater than the mass of the object in a reference frame where it is not moving, the rest mass. Current explanations state that the mass is always the same. The invariant mass and the relativistic effects are described by relativistic momentum and energy. Similar to momentum, kinetic energy has a separate relativistic equation because of the maximum possible velocity of a particle. This relativistic kinetic energy is equal to, we have this little correction factor here for relativistic movement, gamma minus 1, and then mc squared, instead of our Newtonian understanding of energy, 1/2 mv squared. The total energy of a particle is its relativistic kinetic energy plus its rest energy. Einstein's E equals mc squared, which is the energy of a stationary particle. That's the rest energy. So the kinetic energy, which is gamma minus 1 times mc squared plus mc squared. So this simplifies if we distribute mc squared to each of these. Then we have a negative mc squared and a positive mc squared that cancel, and then we're just left with gamma mc squared. With a bit of algebra, total energy can be expressed in terms of rest energy and momentum. Okay, so we can say that E squared, this would be equals mc squared, that's the rest energy. Would be mc squared plus the momentum pc squared, where p is momentum, c is the speed of light squared. By the 1920s, the scientific community had accepted special relativity as the correct way to describe objects in motion. Classical mechanics works with special relativity because, at slow speeds, relativistic effects are very difficult to detect. Einstein was not done, though. In the years following his work on special relativity, he completed what is now called the theory of general relativity. This body of work describes gravitation and further refines our ideas on the passage of time, the geometry of space, and the propagation of light. General relativity is beyond the scope of this course, but it is important to note that what is commonly referred to as Einstein's theory of relativity actually encompasses two related theories: special relativity, describing fast-moving objects, and general relativity, describing gravity.